Right, good morning everyone. The name of this presentation is a replicated object system. This presentation is about the NetFarm replicated object system. The aim of the system is to allow experimentation with writing decentralized programs and protocols. To minimize the time needed to set up these experiments, we want to already have a fault-tolerant decentralized system. This system should allow nodes to join and disconnect whenever, nodes being any computers involved in this network, and for any incorrect computation to be detected. Now, both of these can be achieved using a technique of replication, which is that we store data used in the network on multiple nodes so that they'd all have to go down for it to be unusable. And to allow computations to be reproduced and replicated and rerun on the consumer to check that they are correct if necessary. So the question remains, what kind of computation do we want to run on such a system? Well, hopefully the whole many decentralized programs and protocols gave it away. We want to do all of them. For inspiration, we've looked at old Smalltalk systems, particularly Smalltalk 80, and the affectionately named Blue Book on how it is implemented. The implementation consists of a small interpreter and a small set of primitive operations and runtime, along with an image which provides all the functionality. On the right, we have a picture of this system that I ported a while ago. We can see that there is windowing, we can update code at runtime and do quite a lot of things already. And most of this work is offloaded off the implementer and into the image, which separates the concerns and makes porting it significantly easier. Similar to this approach, we want to use a small interpreter and a small definition of an object system to provide a lot of functionality. So, we already have quite a few decentralized platforms. I can categorize these very broadly. We have some that aren't extensible at all, but they're vague enough to get away with it. For example, the ActivityPub protocol, which is used on a thing called the Fediverse, encapsulates a lot of the actions and the actors involved in many social networks and social media type things. This includes, say, Twitter clones, of which there are a few, forums, and even video sharing sites. While they host dramatically different content, the main mechanisms are the same. We have users, we have collections of media, and so on. There are some platforms which allow any new stuff. Assuming that it might be some client-provided extension, but they can't do any operations on it. This includes the Matrix messaging protocol. What I mean by being able to operate on it is that while they're able to store the information, they can't perform any verification, and if we'd want to do any computation on the server, that is also impossible. Some protocols forbid new stuff, such as the newly popular Gemini protocol, which is a document providing protocol. The reason for forbidding new stuff is to reduce the ways in which it can go wrong. Specifically with the privacy, they want to make sure the system is sufficiently private that it's not possible to leak any user information, and so that it's actually possible to implement. We can control both of these by using a small semantics, like we're saying with this interpreter definition with the Smalltalk model, and we can control both of these. We can eliminate some classes of information leaks by using a small, well-defined language, and we can also make it possible to implement if the language is sufficiently small as well. And of course, we have the platforms that can already operate on new stuff. For example, we have the Ethereum cryptocurrency, where you can write programs called smart contracts, and they can have objects, and you can perform transactions and all that kind of lovely stuff. We didn't go with Ethereum or anything like that because these things tend to be blockchains. because they're very good with the consistency guarantees they provide. However, we did not need such strong consistency guarantees. We could work with weaker, we could work with eventual consistencies, a term I'll get to that later. So we didn't need we didn't need a blockchain, and we would much rather use much less energy, even if that means that we have a weaker consistency model. So the NetFarm project has been the result of almost 3 years of work. Before that, there was a shortly lived Nettle project, and the mistakes in that led us to redesign it and to think quite carefully about how we could produce such a small, well-defined system. I've been to the European List Symposium before for a lightning talk last year. Since then I also went on the online Lisp meeting, and we did a few bunch of releases in the middle. So, first I want to describe how we can implement a NetFarm system. What specifically is interesting about NetFarm? So, our implementation is fundamentally based on a network called a distributed hash table, in which our node computers are organized in a way that allows for storing and retrieving data by searching for a hash of the data. It is a content-addressed system. So, without going into too many details about this, because to be fair, it doesn't really matter about the detail. To be fair, the details of the distributed hash table don't matter. Really, all we need to be able to do is store and retrieve data, and then add our own extensions later on. But to summarize, we know that, of course, we have to be able to store some data on each node for any of it to be accessible. Now, to be able to search for anything, if it's not on this node, then each node will also contain a list of some other nodes. So that if we're looking and we cannot find it on this node, then we can search these other ones. To make this faster, to make it efficient, we also provide some general idea of what data they store. Again, I don't really want to go into details on this, but if you pick the right general idea for this, then you can efficiently search for a node which stores a given data based on the hash. So, the first thing I want to do to make it into NetFarm is that we'll change the data to make them objects in some sense. So we've changed just the bare data we had into what we have just a bunch of slot vectors so far. They can store values and references to other objects. But this alone does not make much of an object system, so what we'll do is we'll add schemas. These are fairly similar to classes, but we used a different term so that we wouldn't confuse ourselves when also discussing classes in the host language. But we'll notice now that if schemas are objects, shouldn't they have schemas as well? Well, sure. We also add a schema which describes a schema, the schema, and this poses an interesting problem. If we're using hashes, then how could we make an object which refers to itself? As I mentioned in the lightning talk, if we try to produce this, well, we find that the hash value of this will invariably depend on itself, and we can't compute that. So, to be fair, for inbuilt objects, such as the schema of a schema, we just cheat. We don't name them by a hash, we just have these symbolic names. But this won't work in the general case. If we want to provide our own structures and our own objects and protocols, we need something else. So, to get to this, first I'd just like to mention one thing about this, what we could draw from the hashes requiring other hash information. Suppose that we have an object A, called A, and it has a reference to another object called B. Then it is fairly clear that to be able to create A, we have to have B already. So the initialization of B has to happen before the initialization of A. Now, if you're reading this, then we write it that way with an arrow because it is quite a lot to write otherwise. So, take the example of the schema again. We'd find that the initialization of S would have to happen before itself, which can't happen. And if we had a circular reference between two objects, then they'd both have to happen before each other, which can't happen. And of course these two are related because the happens before relation is transitive. If A happens before B and B happens before C, then A also happens before C, and you can kind of tell how we can just keep making these loops larger and they still won't work. But of course there's more to it. We couldn't construct any circular references without using side effects or without using a lazy programming language. And many applications require having side effects anyway, so if we have a collection of objects, we might want to add to it later, even though the entire set of those objects isn't defined before. And again, circular references don't work with hashing. So, let's go make some side effects. So, one way that we could have some sort of side effect is to have some transformation on the entire state of the system. This would take one state in, and then it would put out a state with all the effects applied. To make this more modular though, we could split it into one function which takes a state and then produces a bunch of effects to apply, and then we could take an effect and a state and create a state with that applied, and then we can just reduce over that effect list to apply all of the effects. In a real implementation though, we compute the effects for each new object when they come in. We don't do it on every time the state is changed. And we also do some behind-the-scenes trickery to make it work very well with a distributed hash table. However, to make it incremental like this, the effects have to be commutative. So, our way of doing this is that we'll also introduce storage called computed slots to the objects. Each one of these stores a multi-set of values. Multi-set being a set in which you can have an element in the set multiple times. But that's also not quite true, because we also allow negative counts to make it commutative, but many real applications will just treat that as a zero, as we'll soon see. An effect either adds or removes a value from one of these computed slots. So, for example, this would just add. Now, where would we get these effects? We need that first function. Naturally, the user should provide programs to produce these effects. No, not natural? Okay. We use a variation on the SECD machine, a well-known virtual machine for running pure Lisp systems. But we've added provisions for a Smalltalk-like method calling system, and also some way to accumulate side effects. The way this all works is that when an object is initialized on a node, we call the initialize method on it, and then we keep running through that, and we accumulate all the side effects, and then we apply that in the end. To avoid a class of bugs where we have an error for some reason we didn't expect, if a method unwinds, then any side effects it made are discarded, so it could be seen like a transaction in some sense. It either works or nothing happens. And to enforce encapsulation, only an object can emit side effects on itself. If we want an object to emit effects on another one, then it has to call a method. And to make sure that we can't run programs which take too long and use up resources that it shouldn't use, initialization has resource and time limits. So, now that we have a computed value system and computed slots and a virtual machine, we should demonstrate how to make an actual program on it. Here is a picture I took of the element client on Matrix, looking at the net farm room. We have a conversation happen a few days ago, we can see that all these messages are events in a log, and we want to keep these in order. Specifically, we want to see the most recent messages at the bottom of the screen, and the oldest at the top of the screen. So, suppose we're going to make a log on a serial computer. We're not going to worry about concurrency even. We'll have one thread manipulating this log. How could we do it? One way is that we could have a linked list of events, where we have the newest event at the head of the list and the oldest one at the end of the list. We need to keep our reference to the head of the list somewhere. Now, if we want to add an event to this log, it's quite simple. We just put another node, another event, at the start of the list, and then update the log reference. This is maybe a weird way of going about it. You might think that we should use an adjustable vector, for example, instead, because, well, who uses linked lists for this kind of thing? This is to some extent how the concurrent queue in Steel Bank's common Lisp works. I said it was this was going to be a non-concurrent demonstration, but they do some other stuff to make concurrency work, and I didn't really want to show that. Just that we can create such a log using a linked structure and a reference to the head of it. So, how do we go about doing this with replication? Well, let's try to make it work even though it shouldn't. So, we have an event, and the log points to the first event. Right, good. Now, suppose one writer creates an event, and now what it sees is something like this. The log is now updated to point to its head, and of course the event points to the last event. But what happens if another writer comes along and it hasn't seen this yet? Maybe there is latency, or there is a partition in the network. In any case, it can't see it. It still thinks the first event is the latest event. So it goes along and does the same thing. It updates the head of the log, and it also updates and also adds an event. Now, after this partition is resolved, we now have two heads. And, well, we can work with that, because recall that our computed values are multi-sets. We can store multiple values, and that's fine, we can do that. But now, suppose we want to add another event to this. What happens? Which one should it go to? Well, we'll do both. And now we just have one event we have one event coming from the log, and now we have this event pointing to the two last ones. So, in our terminology, we call whatever the log points to the wavefront, and this is allowed to grow if there's a partition or not. But eventually, ideally, we want to keep it as small as possible. So, we could just pin to 1, and it would still work, but the wavefront would still have 2. To keep it down, we try to get an event to reference as many events in the wavefront as possible, as it can see. Now, one thing we'll notice is that if we look at the non-concurrent queue, we can tell that the arrows, funny enough, look like they convey some notion of time. Obviously, the first event happened before the second, and the second one happened before the third. But we have this strange structure in the middle. And, well, this is reflective of the actual reality of the situation. That if neither event observed, if the creation of one event didn't observe the other, then we can't really tell which one came first. So a sorting algorithm that we might use would have to be aware of this, and the user would have to be aware of this, that sometimes in a partition we can't really tell time because, well, there isn't anything to synchronize against. We can't synchronize one against the other. And in this case, we can't, say, assume that we have another observer setting in order. We can implement this in NetFarm. On the left, is the class definition. We use closs and some code written with meta classes to allow this to be translated into a schema. And below this, we see some code I wrote with a program called the Slacker compiler, which takes this schema-like program and generates a bytecode for it. As we can see, we can define methods and call methods on other objects. Now, in a real implementation, we might want to do a few more things. We might want to check if the successor, particularly, say when we have add successor here, we might want to, we could verify that this event is actually well formed, that it will reference us. To do this, in the general case, we can always authenticate the sender by just asking the virtual machine for it. We store a reference to the object that sent the message. There is a way to make the sender anonymous, but we're not going to cover that. And like I was saying before, we could use timestamps to break a tie, such as the one we saw before here. But this would only be to tie break, and we wouldn't generally use that because, well, timestamps can also be unreliable, and in the general case they're not agreed upon. Computer clocks go out. I have far too many clocks in this room, and most of them are out. For your viewing pleasure, we have a disassembly of the remove event function. This is not really anything at all, but I thought someone would want to see it, and I wanted to put it in the paper in case someone wanted to see it, but I didn't do that because it was getting too long. So, what we've shown here is that what we've shown first is how to modify a distributed hash table to make it into something resembling an object system. And we've also defined that something looks like a side effect on this system. And then we showed how to implement part of a real decentralized program. This event graph is precisely what the matrix messaging protocol uses to order some events in the system. What I didn't mention in this is that there are also user objects and digital signatures for authenticating the method call using the sender primitive that I also showed. And these also add some ordering constraints, but they are relevant to our analysis here. We're also able to run netfarm code on the client. We also have these restrictions, and it is inherently a memory-safe language. We cannot do anything bad with it, and it is still confined to the environment using these bytecodes. If we're going to do this, we probably want to disable adding side effects so that we don't do anything that the user isn't expecting, but we probably also want to be able to read the computed slots instead, so that we can present these. Now, there are a few things I still want to do. I'm working on making my implementation of the netfarm system and making it more space efficient. Because if we have all these dependencies that aren't the objects that one node is trying to get, then we might want to get rid of them, but at the same time we might use them later, so I'm thinking that we're eventually going to use some sort of caching mechanism to decide on which ones we're going to keep. I also have a hunch that using our method protocol instead of using data structures like other protocols might give us some more tricks with regards to interoperability, making various programs work together. Speaking of clients, I also want to make a nice looking graphical client. So, that concludes our presentation. I'm not really working on netfarm at the moment. I'm taking a break, but we're still happy to talk about it. We have this room in Freenode and this one on Matrix. They're bridged together so you can pick either one. And we have an implementation, as I mentioned, and I also am working on a specification. It's about halfway there, I'd say. That is all. I hope to see if there's any questions.